Okay, good morning, everyone. Let's continue with our important topic, node voltage analysis. And then the follow-up topic would be mesh current analysis. These are the last two major analysis techniques. They will build off of every technique that we have learned so far. So we'll have to derive equations using KCL, KVL, and solve using those equations. Okay, so let's see, stopped here. Right. Okay. So regarding homework, the topic of node voltage analysis has been introduced. So I would expect students to open up the homework and actually go through at least the tutorial and then start solving problems when I get to the examples. The due date will be finalized once I finish covering the example in class. Okay. So don't be surprised if it's like within a few days. But again, the topic had been introduced last class, so students are expected to, at least open up and take a look at it. All right, so we were here on this slide where I introduced node voltages and talked about the relationship between voltages at every node with regards to a specific reference point. Okay. And there's a purpose to this because the first step in node voltage analysis is identifying all the nodes and selecting a reference node. Okay. Again, as a reminder, voltage is always measured between 2 points. It is the difference in electric potential between 2 points. So we need a reference for measurement. We need a baseline for measurement. In this case, in this example, it's the bottom node. More often than not, it's always convenient to take the bottom node of a circuit as the reference node, especially if there is a power supply attached to it. It just makes things easier. It doesn't have to be the bottom node. It could be any node in the circuit. Okay. All right. So if VA is my reference node and I wish to measure voltages at the other three nodes in the circuit, I can simply write VB, node voltage at VB is simply the voltage measured at B with my reference at A, right? So if this was a meter, I would connect the positive terminal to B and the negative to A, which if you're taking E251, the lab class, you would have done this, right? Similarly, VC is the voltage at C measured with reference to A, and VD is the voltage at D measured with reference to A. Now, these voltages could return a plus or a positive or a negative number. Okay, that doesn't matter. When you write out the equations, you would simply plug in that positive or negative number in there. But when you measure and when you're writing out the values for each of these node voltages, it is always with reference to the node that you selected. Okay, so VB is VBA, VC is VCA, and VD is VDA. Now, we talk about resistor voltages. We can describe each resistor voltage in terms of the node voltages. Let's take a 10-second pause while you think over the node voltage concept and let me know if you have any questions. Any questions at all? I'll move on. Okay. All right, so resistor voltages. Here, I have three resistors, R1, R2, and R3. R3 is actually not noted, but let me write it down. And they have the corresponding voltages V1, V2, and V3. Now, in this illustration, the circuit schematic already has the polarity of the voltages given to us. If it was not, we would make an assumption, right? The power supply is shown to us with a plus on the top and minus on the bottom. So current goes in this direction. If current goes in this direction, then the point of entry is positive. Current keeps flowing down this way. Some of it goes down here. Again, point of entry is positive, and that's why we have these signs on the resistor voltages. Right? Always keep that in mind. Okay, so now we have resistor voltages V1, V2, and V3. Voltage, again, is the difference in electric potential between 2 points. So a resistor voltage V1 can be described as the difference in potential between the outer ends of that resistor, meaning B and C. This is very critical because this is how you will write out the equations. Okay. Again, resistor voltage can be described as a difference of the voltages at each end of that resistor. As an example, if you're talking about V1 is for resistor R1. Resistor R1 is connected between B and C, nodes B and C. We have already established that node B, or established or assumed at the beginning of our analysis, that node B is at a higher level than C, right? We have a plus at B and a minus at C. So we would write out V1 as the difference between B and C. And since I had assumed B is higher than C, I would write it as VB minus VC. Does that make sense to everyone? Right? Resistor voltage can be described in terms of the voltages that appear at either end or both ends of that resistor. Yes. Yes. So the question being asked was if there was a resistor between the negative terminal of the power supply and the node A at ground, and whether the voltage at the top end of the resistor would be negative, and the answer would be yes. And we'll see that in the example. We'll see that in examples coming up. Okay, so where was I? Oh, yeah, V1 is described in terms of node voltages VB and VC, which is right here. And so similarly, I can write out V2 as the difference between the node voltages C and D. Okay, C and D. And so my V2 right there is VC minus VA. Again, VC, oh, sorry, pointed out the wrong resistor. V2 is here, R2. And so VC and VA. So V2 is the difference between C and A. And so I can write V2, the voltage across resistor R2, is a difference between the node voltages VC and VA. VC and VA. And then same thing for V3. V3 is the difference between C and D. And so I can write V3 is VC minus VD, which we can see right here. And same thing for V4. V4 is measured between D and A. Resistor R4 is connected between nodes D and A. And so V4 is VD minus VA. Does that make sense to everyone? Let's take a 10-second pause. Think over it. Let me know if you have any questions. Yes. Don't worry about mesh currents now. That was just for introduction, introducing the topic, but we'll look into mesh currents when we get to mesh current analysis. Yeah. Right now, mesh currents don't have anything to do with node voltage analysis, so we'll leave that on the side. Yes. Sure. Sure. So the question being asked is, why did we choose A as a reference? Several reasons. One of the first is, if a node is connected to a power supply, and that's a point that would come in a couple of slides, but if a node is connected to one end of a power supply, you automatically have the value for the other end of the power supply. Okay, so think about it. If I choose A as my reference node, then I already know what the value is at VB, at node B. Because node B is connected to the other end of a power supply. So the difference in potential between B and A is VB minus VA, which would be the power supply VS. So that is one of the biggest reasons to choose that. The other reason is, if it's a bottom node, which is connected to a number of components. So in this case, A is connected to the power supply plus R2 plus R4. And so it just makes logical sense to choose that one, because you can describe two resistor voltages using that node. We could also choose C as a reference node, but it just means we would have to write more equations in order to obtain our value. Did anyone else have a question in the back? Okay, so is everybody clear on resistor voltages versus node voltages, and how to describe resistor voltages in terms of the node voltages? And this is the foundation of node voltage analysis. So we would apply KCL in conjunction with node voltage analysis techniques to write out equations. The equations would have variables. The variables in this case would be the node voltages, and then we would solve these simultaneous equations to obtain values for those node voltages. Once we have the values for those node voltages, we can find any other voltage or current in the entire circuit. And that is the analysis technique. Okay, our job is to write out equations, and the equations will have variables. The variables in this technique are the node voltages. So how do we write out equations? Well, here's an example with a single resistor right here. I have node voltages VA and VB, R, resistor R, and the current direction given here. So my current is flowing from left to right. Which end is positive? Which end is negative? Left or right? Left side, right? Point of entry is always positive. So voltage VR has a polarity of plus on the left and minus on the right. I can write VR is equal to VA minus VB. VR is VA minus VB. Everyone with me so far? Okay. Then you apply Ohm's law and you write an equation for I. V equals IR. I is equal to V divided by R. And so that would be VR over R. Substitute VA minus VB in there, and you have your equation. Well, not the equation, but the representation for the current I. Ten-second pause. Think over it. Let me know if you have questions. Yes. Yes. And we'll expand on. So this is first step. Then we get to the next step right here. Then we'll have multiple equations. Yes. Yes. Good point. Again, because it's a difference between A and B. So we can write VAB is VR. This is a side note. Plus and minus, two subscript notation. Okay, so the next step in this circuit, we follow the same assumptions. Point of entry is plus. So I'm going to say voltage across R1 is VR1. Voltage across R2 is VR2. Point of entry is plus, exit is minus. And this is VR3, plus on the left, minus on the right. Just as a side note, I prefer to use the full name of the component. So the component notation is R1. I like to say VR1 and not just V1. It just, chances of messing up or making things clear is much higher. And so I like to use the full name. So the two subscripts you see in there, VR1. Again, I pointed this out earlier in first week, that R1 just simply stands for the notation for that component. Okay. Okay, so we have VR1, VR3, and VR2. Okay. So when we want to write out the equation, what we are doing is we are writing out the equation at each and every single node that is present in the circuit. So in this case, that's the center node at B right there. I will write a KCL equation at node B. KCL at node B. KCL, currents entering is equal to the total currents leaving. So I1 is equal to I2 plus I3. Okay, I1 is equal to I2 plus I3. Then I1, again, and some students skip a step here, but I would always strongly advise not to skip the step. I1 can be written as VR1 divided by R1, VR2 divided by R2, and VR3 divided by R3. So this is the step where you apply Ohm's law, right? So this is KCL. This is Ohm's law. And remember, I harp and emphasize saying that this class, more than others, is built step by step, meaning everything that we learn at the beginning of the class, every analysis technique will be built upon, and we will use those techniques again and again. Okay, so we first learned about Ohm's law, then KVL, KCL. Now's the time we use those to solve for larger circuits. Okay, once we have this, we then describe each resistor voltage in terms of the node voltages. VR1 is VA minus VB or R1. VR2 is VB minus VC or R2. And VR3 is VB minus VD or R3. And that's it. That is our equation. Node voltages. At this point, node voltages are unknowns. So VA, VB, VC, VD are unknowns to us. We haven't, I've not talked about reference node. This is just an example of how we would write up the equation. Okay, the steps involved in writing the equations. Once we are done writing out this equation, we would plug in all of the known values. The resistor values are known to us. They will be given at the beginning of the problem. So you plug in all the known resistor values, plus if you have a power supply in there, you would know the answer to one of these node voltages. Okay, right now we have 4 unknown variables, A, B, C, D, V, A, B, C, D. We might, if you have a power supply connected at one of these nodes, we would have an answer for that. So let's say VA had a power supply connected to it. Then VA would be known to us. And if we chose C as a reference node, then what would be the value for VC? 0, because that's a reference node. For the purposes of the analysis, at the beginning of the analysis, we are choosing VC as the reference node. Whichever node you choose as the reference node will have a value of 0 volts for that particular analysis. The actual voltage does not matter. Okay, this is purely theoretical or hypothetical, if you want to call it that. So that is a very important point. The reference node always 0 volts for that analysis. If you choose node B as your reference, then VB for that analysis will be 0. Your equations might look a little bit different, but the answer at the end would always come out to be the same. Doesn't matter what you choose at your reference node. So 10-second pause. Let me know if you have any questions. Again, I'm taking this a little bit slowly, taking it step by step, but when you practice this with the homework, the point is that students should be able to do this efficiently, quickly, and correctly. Does this make sense, everyone, right? Okay. So then VA would be known to us if there's a power supply connected to it. VC is 0 volts. So out of 4 variables, I have my answer for 2 of those. So there are only 2 unknown variables left. If there are 2 unknown variables, how many equations do I need? 2. That's it. So you write out a second equation at another node, and then just solve it that way. You can write as many equations as the circuit and as you want. If there are like 4 nodes on there, you can write 4 different KCL equations. But, again, efficiency. So efficiency would mean as an engineer, you need to find a method that works and a method that works with the least amount of resources. So instead of writing 3 equations, you just write 2. Make sense to everyone? Okay, any questions? Online students, any questions? Okay. So to sum up, the first step is to identify all the nodes in a circuit and select a reference node. Most important, reference node could be any node, and it will always have a value of 0 volts for the purposes of that analysis, purposes of that specific analysis. Then you assign branch currents to all branches, which is what we did with I1, I2, I3, and I4. Pretty much there'd be resistor currents. And you apply KCL at each and every node. Well, When I say each and every node, depending on how many variables you have. Depending on the number of variables, apply Ohm's law and express each voltage in terms of the resistor voltage in terms of the apply Ohm's law and express each of the currents in terms of the voltages. Okay, that is the step I said that students tend to skip as they get more and more adept at solving these equations. They just tend to skip that step. But I always strongly recommend do not skip. This minimizes your chances of errors. So you should always write out that equation. And then as a final step, you express each resistor voltage in terms of the node voltages. And then you solve for the node voltages. Node voltages are the variables. Everyone clear on the steps? So these are guaranteed on the final exam. The one problem, it'll be part of a larger problem. And this technique is guaranteed to be there on the final exam. Okay. If you haven't yet checked it out, the final exam page has been online on the syllabus since the first day of class. And I outline what topics will be tested and assessed. Okay, let's move on to the example. So, question being asked is solve for all branch currents and the node voltages. Now, the question does not specifically ask you to solve with NVA, but this is an example about NVA, so we are using NVA techniques to solve this. Okay, so this is I like to use this example because it's very interesting. You have two current sources in there, no voltage sources. Makes things easier actually, because we're writing KCL equations. So if we have current values in there, we already are halfway there, so to speak. So two current sources, one is going up, one is going down. Values for both are given to us, 10 and 50 milliamps. And then there are 4 resistors in the circuit. What do we see? Right at the beginning, what do we see with regards to the resistors? What jumps out? Anything? R2 and R3, they are in parallel. So even before you begin your analysis, you can reduce R2 and R3 to one single resistance. So let's redraw the circuit. And I would call that R4 is already there. So let me call this R23. And R23 is the parallel combination of R1 and R2. So depending on the circuit, again, your first step could be a little bit different. Our first step for NVA, of course, is to identify all the nodes in the circuit and then choose a reference node. So how many nodes in the circuit? Take your time. There's no penalty for a wrong guess. So take a guess. An educated guess. Yes. This is 6. 6 is the logical conclusion. 4. 4. I heard 3 there. Anyone else? 3? Should maybe take a poll. So let's take a look. Three. At first glance, the circuit schematic is drawn in such a way that we think that every dot is a node, which is quite normal. But when we take a look at the wires, if you look at the connections for each resistor, they're going to the exact same junction. And remember, fundamental point, doesn't matter how long the wire is. Could be a dot, could be a short dash, short line, or a very long line. They are all exactly the same. Again, the example of a power extension cable. If you plug an extension cable into a wall outlet and you bring it out 100 feet, you would still be able to obtain power from it. It's still the same as a dot. Okay. So there are 3 nodes in the circuit, and our job's easy now because we choose one reference node. And in this case, I'd like to choose the bottom node. This symbol is given here, but even if it wasn't given, I'm going to choose the bottom node as my reference node. So I'm going to label this top left as A, top right as B, and the bottom node as C. Okay, so A, B, C. I have 3 resistors, so I can write out equations at each of the other 2 nodes. So choose C as reference, and therefore VC is equal to 0 volts. VC is equal to 0 volts. Now, beginning of the analysis, we have no idea of the resistor polarities. We have resistor voltage polarities. We have no idea of the current directions. And in this case, and this is one of the reasons I like this, current I1 is going up, current I2 is going down. So some of the values we choose will end up being negative. So let's solve and let's find out. So I1 is going up in this direction. So I'm going to choose current flowing through R23 is going from left to right, and I will call it IR23. Okay. Again, 3 notations. 3 subscripts, but again, it just notes current for the resistor 23. Then current for resistor R1, I'll choose as going down. I'm going to call that IR1. This is current source I1, current source I2. R4 is interesting. The current from I2 comes this way. It could possibly go up here, but we also have this current coming here. So which one to select? It's an assumption. You can select anything. You can select going down, going up, doesn't really matter. But the important point is, once you select a direction, once you make an assumption, you stick with that assumption for the entirety of your analysis. You do not change that assumption halfway through your analysis. Otherwise, you'd end up with the wrong answer. So let's see. I'll choose going down, just to keep things consistent. So I'll choose going down. So that is IR4. IR4 going down. So IR1 and IR4 are both going down. And now I'm ready to write out my KCL equations at both B and C. I can write out a KCL equation at node C also, but write it out at A and B. So apply KCL at node A. I have current I1 entering the node. IR1 and IR23 are leaving the node. Let's make this bigger. IR1, IR23. Good. So we have our KCL. Now we apply Ohm's law and describe each of these resistor voltages in terms of the resistor. So IR1 is VR1 divided by R1 plus VR23 divided by R23. Then I1 would be equal to VR1 is now the difference between A and C. Okay. VR1, the difference in the node voltages between A and C. And so I can write VA minus VC or R1. It helps if you wish to put a plus and a minus sign. So since I chose the current going this direction, the voltage would appear with this polarity. Again, these are assumptions on our part, right? And so if the current is going this direction, you got plus and minus. So that way I know which node is higher and which is lower. Then plus VR23 is VA minus VB divided by R23. Plug in all the known values. I1 is given to us as, what is given? 10 milliamps. So 0.01 is equal to VA minus VC. VC is 0 volts, so it's VA divided by R1. R1 is what? 1 kilo ohm, 1000. 1000 plus VA minus VB. Oh, R23. You never calculated R23. R23 is parallel of 2000 and 10,000. So anyone have those numbers for me? It's 2000. Anyone doing this calculation? Is that number correct?
Yeah, that's right.
Thank you. I tend to take like 3 or 4 decimal places just so my final answer is more accurate. But 2 or 3 is fine. All right, so I would write out the equation and I would get, let's just multiply multiply by 1,000. Let's see. Once you have the values in there, you can solve the way that that you're comfortable with. So I tend to do this, multiply everything by 1,000. So I get, let's see, 100, no, sorry, 10 is equal to VA plus 0.599. Okay, combine it so that my equation is only in terms of the variables. That's equation number 1. Let's take a 10-second pause. Let me know if you have any questions. Has anybody else solved it? I mean, solve for these values. Okay, I'm going to go a little bit faster when I apply KCL at node B. So KCL at B would give me, what is the equation? Let's see. I have IR23 entering, IR4 and I2 are leaving. So I would write IR23 and IR4 plus my current source I2. IR23 I can write as VR23 divided by R23 VR23 is VA minus VB divided by 166.667, and VR4 is 2 VB minus VC, and R4 is given to us as, let's see, 2000. So 2000 plus I2 is 50 milliamps, so 0.05. Yep, 0.05. And now multiplying everything by 2000, what do I get? If I take it on the other side, I would get 1.19 VA minus 2.199 VB is equal to 100. Someone solve these two equations for me, please. Once you have these two equations, you can solve them with any technique you want. My calculator is from the 90s, still works. It is not programmable, so I solve them kind of like manually. But from this point, simple, I guess, middle school math, I want to say. Does that make sense to everyone? Point of the analysis technique is to write as many equations as there are variables, or basically enough equations to be able to solve for the values for those variables. In this case, I have 3 nodes. One is my reference node, so I have 2 unknown variables, VA and VB. And so I would like to write 2 equations. Once you have those 2 equations, solve them with any technique you want. You can solve them using a calculator directly. You do not have to write out steps. So at this point, you can simply write out the final answer. Again, if you have a programmable calculator where you can program these 2 equations in there, it will spit out a value for VA and VB. How many of you do that? I've actually never done that because I don't have such a calculator, and I don't want to actually learn new technology now in that sense. But is everybody good with this? Any questions about the technique? Node voltage analysis. Okay. Has anyone solved this? Anyone? Online, in person? If anyone has solved it, please let me know the answer. Think over the technique. Let me know if you have any questions. That's fine. Could be negative. That seems about right. I think it was in the 40s and the 50s. I'll have to check I forgot my notes, but I think these are correct. Let me see. Anyone else? Well, let's just say these are the right values. All that means is that both points A and B are at a lower value than C. And which is certainly possible because if you look at the current directions and the values, this is 50 milliamps, this is 10. So current is going in the downward direction of the circuit. It's going towards node C. It's going toward node C. If it's going towards node C and it is at a higher value than I1, chances are that the current is going in this direction. And so point C or node C would have a higher potential than nodes A and B. Does that make sense to everyone? Right? So again, it doesn't matter what our assumptions are at the beginning of the problem. If you stick with your assumptions and you do the analysis correctly, you will end up with the right answer. So again, I'll check with my notes, but I believe these are the right answers. And once you have VA and VB, hold on. Once you have these values, plug back into the KCL equations. And once you plug it back in there, you'd be able to find the values for everything. All the resistor voltages, all the resistor currents. And that is the purpose or the point of the analysis, to find the unknown voltages and currents that appear in the circuit. Okay. So consider the homework on node voltage analysis as assigned. We have completed that topic. Okay, the due dates will be, well, I will post the due dates, but I probably might keep it like Saturday Saturday or Sunday. Okay. All right, LN class here today. Let me know if you have any questions. Otherwise, I'll see you all on Friday.